I'm not going to try to pronounce any names here, but this is an end-to-end flight software development cycle presentation. Right? That's yours? Okay.
Oh, this one? Hi. Okay. Thanks. So good afternoon, everyone. My name is Mar, and today I'm going to present the end-to-end flight software development cycle for an interplanetary spacecraft mission in which LASP and the AVS laboratory at CU Boulder are collaborating. And we're going to see the complete flight software development cycle for this mission. So we'll start with the desktop algorithm design using the Basilisk software testbed. We'll then see migration from the Basilisk desktop environment into the core flight system middleware. And then we'll see embedded testing of the CFS flight software application in an emulated FlatSat. And a couple of interesting aspects about this cycle are the transparent migration from desktop into CFS and consistent testing throughout testbeds by means of a distributed communication architecture. So this slide shows the development cycle illustrated graphically. And we're going to start with the Basilisk framework, where we prototype the flight software algorithms. We then migrate these algorithms into the core flight system in a transparent manner, and transparent meaning that the source code does not change for migration. And then we are ready to embed the CFS flight software application into a single board computer emulator in order to perform distributed closed loop testing. And I would like to start with an overview of Basilisk, which is an open source cross-platform desktop testbed for designing flight algorithms and testing them in closed-loop dynamic simulation. So Basilisk leverages the use of Python for flight software development, provided the flight algorithm source code and the spacecraft simulation code are written exclusively in C and C++, and then simply wrapped into Python for setup, desktop execution, and post-processing. And this image over here shows the nominal configuration of a Basilisk simulation. There's a dynamic process containing spacecraft physical models written in C++ and a flight software process containing the mission-specific GNC algorithms written in C. And Basilisk is architected in a modular fashion, and during a simulation run, all these C and C++ models interact with each other through a message passing interface, or MPI. And the beauty of this MPI is that it marks a clear separation between the two processes. And this separation later on facilitates the migration of the flight application into a different processor. So Basilisk developed flight algorithms have imported to both commercial processors like the Raspberry Pi, but also to a couple of different middleware layers like the core flight system and more recently MicroPython. Although today I'm going to focus on CFS specifically. So what I'm going to describe next is what does it take to migrate the flight software algorithms from the Basilisk desktop environment, which is a combination between Python and C, into a pure C flight software application that can be readily integrated into CFS. So if you recall, Basilisk leveraged the use of Python for flight software setup, desktop execution, and post-processing. And there is one of these functionalities that needs to be translated from Python into C in order to come up with a complete pure C application. And this is the setup. And in the Basilisk framework, the setup code encompasses module variable initialization and task definition. And now we're going to see each of these two items one by one. So we'll start with the C module initialization. A Basilisk model can be seen as a standalone model or piece of self-contained logic. So in the context of flight software, this could be a specific navigation filter, a very specific control flow. And here I'm showing an example of a very simple model, the vehicle configuration one, which simply contains vehicle static data that in a simulation run will be used by other models. All Basilisk models are characterized by having a configuration struct and 4 generic algorithm calls, self-init, cross-init, update, and reset, that are called from Python during desktop execution. So all these C models are wrapped in Swig and made available at the Python layer for initialization. And here we see the Python instantiation of the vehicle configuration model, as well as the initialization of its variables, inertia, center of mass, output message name. The second item that we handle through Python is the definition of tasks that run at certain rates. And any number of models can be added to each task. So here, there is an example of a Python instantiation of a flight software process, the creation of an initialization task, and the addition of the vehicle configuration data model into these tasks. So we have just seen which is the setup code that needs to be translated from Python into C. And a key remark here is that only the setup code needs to be translated for migration, and the flight algorithm source code remains unchanged. So the pure C flight software application is conformed by the modified flight algorithms plus 1 header and 1 source file containing this setup code. And the interesting part of the story is that the translation from Python into C is handled automatically via a third-party script, the AutoSetter the Pi, that we've developed for this purpose. And the beauty of the AutoSetter the Pi is that it's not a black box. It's different from autocoding in the sense that it's a very simple and transparent template that simply maps Python variable types into their C counterpart. And the resulting C setup code, it's minimal and looks like optimized human-written code. And the trick behind the AutoSetter the Pi is that Python is great at introspection. So Python is great at looking at itself. And introspection is something that cannot be achieved just with C and C++ without a significant effort in source parsing. So here I'm showing code snippets of the Python input to the AutoSetter the Pi and the C output. And because Python is great at introspection, the AutoSetter quickly realizes that in a given Python scenario script, there is a flight software process with this vehicle configuration model, and that some of its variables are actually initialized with non-zero values. So if we take a look at the inertia, for instance, in Python, this is initialized as a list of 9 floats, and the AutoSetter knows that in C, this unambiguously translates into an array of 9 doubles with only certain indices initialized. And this is a very simple example, but as long as you handle recursion and nested structures properly, in the end, the C variable types, they always boil down to the same ones. So the beauty of the AutoSetter is that it's very simple, but it's very powerful because it enables rapid iteration of the flight configuration back and forth desktop and embedded environments. So it's really a time saver. And now we've just seen, which is this, now we have seen that this setup code plus the modified flight algorithms conform a pure C flight software application, which we can then integrate into CFS and perform embedded testing. And in particular, I'm going to talk about embedded testing of the CFS flight software application in an emulated flatsat. So in such configuration, CFS flight software runs within an SVC emulator and interacts with external world models for closed-loop testing. However, once flight software is integrated into CFS and embedded into the SVC, it's no longer as simple to access the flight software states for reading and writing. And for this reason, it has been necessary to emulate the FPGA registers within the SVC emulator as well. And before describing further this FPGA register space, I would like to step back and talk about the specific flat-sat models that we use and the distributed communication architecture that supports this emulated flat-sat. So for this spacecraft mission, the general concept of an emulated flat-sat has materialized in the configuration that is shown here. So the flight processor emulator we use is the open source QEMU. And we're emulating a Leon 3 board with RTMs running on top. Inside QEMU, there's also the CFS flight software executable, as well as the modeled FPGA registers. The spacecraft physical simulation we use is Basilisk, which handles dynamics, kinematics, and environment, but also models sensors, actuators, and complex avionics hardware. The ground system emulator we use is a LASP in-house model named Hydra, which contains the command and telemetry databases for this mission. And the visualization is an open source GUI that is available together with Basilisk. So the challenge of enabling communication between all these models is that all these applications all these are standalone applications that were never designed to work together. So they are completely heterogeneous. They are written in different programming languages, C++, C, Python, C#. They have different execution speeds. So some of them are asynchronous, like the ground system, which is event-driven, while others are synchronous, like CFS flight software or the spacecraft physical simulation. But even among the synchronous ones, they have different execution speeds. So QEMU, for instance, runs slower than real-time, but Basilisk runs natively way faster than real-time. In addition, some of them are multi-threaded, while others are single-threaded, which is something important when you think about communication and socket connections. They also have different endiness, which is especially tricky to handle. So the integration of independent spacecraft mission models into a single simulation run demands for a solid communication architecture underneath. And on these lines, I'm going to briefly talk about Black Lion, a purely software-based communication architecture that we have developed in support to this mission. So Black Lion aims to achieve 4 communication goals. The first is the transport of binary data between nodes or applications. The second is serialization of binary data. So each application needs to know how to translate the received bytes into structured data that it can then handle internally. The third goal is synchronization. So all these components need to be kept in lockstep during a simulation run. And the fourth goal is to have dynamicity in this connection map. This means that none of these applications should be required. All of them should be like clients that can come and go without bringing down the entire system. So Black Lion aims to achieve these 4 communication goals while remaining as abstracted as possible from the internals of each node. So this means that we don't really want to heavily modify the source code of each application. And with this purpose in mind, Black Lion has been designed with a unique central controller and 2 APIs, the delegate and the router. Both of them are attached to each of the nodes. So the central controller acts as a message broker and a master for synchronization. The delegate API manages sockets and direct connections with the central controller, and the router functionality is to route internal data in and out from the node's internal. So Black Lion uses a tick-tock mechanism in order to maintain all the nodes in lockstep and achieve synchronization. So the central controller sends a tick command to all the applications, and then each of them publishes its own internal data. It subscribes to fresh data from the external wall, and if the application is synchronous, it steps forward for the commanded time step. At the end of this, each application talks and sits there waiting for the central controller to send the next tick, which won't happen until all the applications have talked. So this is how we achieve the lockstep. Okay, so this has been an overview of the Black Lion communication architecture, and from now onwards, I'm going to represent this distributed communication with this simple TCP sign. And what I would like to focus on is on the FPGA registers that we have modeled within the SBC emulator, because all the flight software states that need to be shared with the external world, they are mapped into these registers. And we have modeled a total of 4 register boards, and each register has a memory buffer associated, so the shared flight software states are mapped to this buffer. And I'm going to refer to these shared flight software states as snorkels, in the sense that they are direct connection pipes to the internals of the CFS flight software application. So through these registers, flight software reads and writes in a hardware-like fashion that also replicates board interrupts. And together with the register modeling, we have expanded the spacecraft physical simulation with complex avionics hardware, which leverage some functionality that would otherwise have to happen within the register space as well. So a couple of examples of these avionic hardware models are the PCU, responsible of managing controller, switch, and propulsion cards, or the IPC, responsible of retrieving and storing NVM commands and producing housekeeping packets. So within each register space, we have modeled a bunch of snorkels. There are snorkels related to actuators, like reaction wheel commands from flight software, reaction wheel speeds to flight software. There are snorkels related to sensors, like the Corsan sensor or the star tracker. We have snorkels related to the Avionics model, PCU, IPC. We also have snorkels related to time. There are a couple of clocks, the master VTC clock and the slave VTC clock. And we also have snorkels for command and for telemetry. And the trickiest part of all these snorkels is that each of them is pretty unique. So they share some basic features, but their internal operations are completely different. So some of these snorkels are unidirectional, either readers or writers with respect to flight software, while others are bidirectional. Some of them operate only on a packet address, while others also need an address, a descriptor address, where the descriptor is describing something important about the packet. Some snorkels store single word packets, while others need to queue them up. Some of these packets have fixed size, while most of them are variable sized. The snorkels related to command and telemetry need to also add or remove byte headers to the packet depending on the, depending on the direction. And most of them need to handle NDNS because QEMU is little endian. So now I'm going to show a couple of numerical simulations which showcase the use of these registers. So the first simulation will encompass several spacecraft pointing maneuvers that are manually triggered by the user using the command database interface. So we'll see how the user enables flight software monitoring, commands the spacecraft to inertial pointing, correlates the ephemeris, commands Mars pointing, switch to SAM pointing, and back to Mars pointing. And the second numerical simulation will be a video of Mars orbit insertion. And a few interesting things that we'll see is a time jam. So we'll put the spacecraft into a sort of wormhole and bring it right before MOI. We'll also see the delta V burns, of course, which are related to the propulsion cards within the PCU. And most interestingly, we'll see a lot of nominal testing, where there will be several modeled flight software resets and of nominal star tracker acquisition. But before that, we'll start with a spacecraft pointing maneuvers. So these plots show the evolution of the spacecraft. Principal attitude in a simulated closed loop, as seen by the spacecraft physical simulation. So the spacecraft initially starts at a certain attitude with flight software not yet doing anything, and then the user enables flight software monitoring, and it commands the spacecraft into several pointing modes. And during this closed loop run, again, all the flight software states, like sensor data, command, telemetry, reaction wheel torques, they are all stored in these registers. It's not working. I'm not sure if there is another slide or not, but we can switch to the video, that's fine. So the video is the second, yeah, there we go. So the video is the second numerical simulation I'm going to show using the visualization in a closed loop. And here we start pretty far away from Mars, and we see the time jump. We bring the space. Let's see. Okay, there we go. So we bring the spacecraft right before MOI, and we're trying to stabilize its attitude in order to start the burn. So this should happen soon. There we go. Now we will start the delta V burn, but there will be a flight software reset. And we come back again. And the spacecraft will try to stabilize its attitude again, but the start trackers are not reconfigured properly. So we'll see the spacecraft has a hard time resuming the delta V burn. There will be more flight software resets. So as I mentioned, this is a pretty of nominal testing. But we made it there. And there we go. We start the DV burn again. Yet there will be yet another reset. But we resume, and now if we scroll, if we zoom out, we'll see that the hyperbolic orbit, if you can see that, will become elliptical, and the orbit will start shrinking down, and yeah, we're finally captured, and that's the end of the burn. So yeah, that's all I have. And if you have any questions, I'll be very happy to take them. Thank you for your attention.
Thank you. Glasses, someone lost glasses. Someone handed them to me earlier. They're Foster grants. If you lost some, come see me. I'll get them to you. By the way, it's snowing outside. So we went from 50+ degrees yesterday to snow right now. So less than 24 hours. So welcome to Alabama. So we're going to not postpone. We're going to not have any time for questions. Okay. So our next speakers are